My name is Darius, and my talk today is about exploring some of the dark corners of C# as a programming language. It is a common platitude to claim that C# and Java are very much the same language, and there's a case to be made. I mean, they're both object-oriented, they both have a garbage collector, they both support interfaces. Even syntactically, they're pretty amazingly similar, and it's a common wisdom to say, well, that the difference is merely commercial more than a technical issue. In this talk, I submit that there is more than meets the eye, and that there are intrinsic differences in between these languages that make them very, very different, at least for a very specific use case. In order to adequately make the case, though, please give me some time to present what it is we do at Raincode Labs and set up the context where these differences between Java and C# will be more apparent and more obvious. So in a nutshell, if I were to brag, I am bragging actually, Raincode Labs is by far the largest independent compiler company in the world. And when I make this statement, most people assume that what we do is, I don't know, LLVM retargeting and low-level optimization. And there is that, of course, but in fact, Raincode Labs is way more about applying compiler-related technology than about compilers per se. One of our major activities within Raincode Labs is to translate software systems from one language to another. And from a distance, this looks amazingly like compilation. When I interview people and I say, what's the difference between translating an asset from this language to Java and a compiler, they all think they're all being very smart and say, well, that's essentially the same because in both cases you're translating, and that's true. But there's an intrinsic difference between both approaches. When you compile, all you do is produce code that's going to have the same behavior with adequate resource consumption and adequate performance, and everything else doesn't matter. When you translate from one language to another, it's not just a machine that has to consume the result of whatever you do, it's a human programmer. So readability, structure, maintainability are very important, while from a purely compiler point of view, they really do not matter at all. For instance, and I could come up with dozens of similar cases, when you generate intermediate C code as part of a compilation process, you typically generate tons of extra parentheses and tons of extra braces and tons of extra identifiers even, because who cares? Nobody's going to read it. If the code you generate is meant to be maintained further by human, all these things are getting in the way. All these things add to the entropy of the resulting software system. All these things have a dramatically negative effect on the value of your translation. For instance, when compiling, inlining is like the most obvious optimization in the book, essentially replacing calls to a function by the function's body, because elaborating the parameters is too costly, and it makes for a very sensible optimization. When we translate from one language to another, that's exactly what we try to never do, because you are essentially increasing entropy. Instead, you're getting rid of the functional abstraction that helps the human programmer maintain that code from there on. And inlining is only the tip of the iceberg. Comments have to be preserved. Identifiers must make sense. Sometimes you have to synthesize identifiers because you're representing stuff that did not exist in the original program, and you have to make sensible synthetic identifiers. All the things you do in order to make the code look more and more like something a human programmer would have written in the first place and can therefore proficiently maintain. So source-to-source translation is in fact very different from compilation. At the end of the day, it's going to be a balancing act. Because you essentially have two target audiences to please. You can try to please the people who were maintaining the system before the migration, and then the clarity of purpose must be there, the original concept must be reproduced as is. Or you may try to accommodate, let's say, the target audience, the developers that are proficient in the target language, and produce something that is as idiomatic as possible in this target language. And like many things in the real world, at the end of the day, it's going to be a compromise, it's going to be a balancing act. You're going to have to support both approaches. Thinking that you can support one at the expense of the other with no limit inside is unreasonable. As a matter of fact, in our industry, we don't do this, but a number of people do COBOL to Java migrations. I think it's a very bad idea, and this is beyond the scope of this talk to get into the details of what it is, why it is indeed a bad idea. But for those kind of people, there's a moniker that has come up with called JOBOL. It's technically Java. It's recognizable by a Java compiler, but it's so crippled with COBOL concepts that only a very proficient COBOL developer can maintain it. Knowing Java idiomatically is not enough to be able to maintain those systems. Another misconception is about the simplistic nature of the process. Seen from a distance, you say, well, I'm going to write something that's going to take the input language and that is going to recognize technically we call that obviously a parser. We're going to parse the original program, we're going to recognize it, we're going to perform semantic analysis, and from there we're going to generate the resulting system. And that's it. And that's the end of it, really. That's La La Land. That's fantasy. That's not the way these things go. This simplistic picture fails to recognize that you are tackling an incredibly complex problem because you have a single pass, you have a single translation process that has to support all the idiosyncrasies of the original language. And in a single step, transform all the constructs of the original language into constructs in the target language that must be of the best possible quality out of the box. And those two sets of constraints, those conflicting constraints even, make for a totally unreasonable proposition. In practice, we're going to divide and conquer. In practice, we're going to divide this pretty complex problem in smaller steps. And typically what we will do is that we will implement transformation, typically simplistic transformation within the source language, where we're going to take programs in the source language and reduce their entropy, make implicit constructs explicit, reduce constructs that are barely used, reduce them to other ones. To a vast extent, I would call that reducing the source system to a canonic form with a limited set of features. And by doing this, by limiting this set of features, it makes the translation process simpler because there are fewer constructs to support. And because we are essentially talking about transformation within the language. For the sake of the example, if we were to translate Fortran to Java, before going through the translation per se, we're going to have Fortran to Fortran transformation to reduce the number of Fortran constructs that our translator has to support. Interestingly enough, since we are all still within Fortran as a language, it means that the intermediate steps can be tested for functional equivalence. And this is really not rocket science. Some of these transformations can be amazingly simple. Can be as simple as an awk or sed script. Can be a text processing thing. It could be reformatting comments. It could be really very simplistic. There is really this idea of dividing and conquering our problem into something more manageable, because simplifying the input makes the translation process much simpler. You can now guess what comes next. Just as we simplified the problem at the input side, we can improve on the output side. Instead of having our translation process generate the best possible output in one go, we can generate something elementary, something simpler, something functionally equivalent, something that will execute and have the same behavior, but that is not meant to be maintained necessarily as is, and have post-processing transformations that will take that rough cut, that rough output of the translation process, and try to improve it in order to make it closer and closer to what a human developer would have written and can therefore maintain. That can include getting rid of additional constructs, dead code, additional parentheses, pretty printing even sometimes can be really idiotic. This gives you like a better picture of how this world of language-to-language translation works. It's at the same time very complex, and I think I made the case that it is very different from plain compilation. So this is the scene. This is what we do. This is how source-to-source translation work in the industry. And I guess you can appreciate how different it is from compilation. It is in some sense simpler because we have the ability to divide and conquer the way I described. And it is in some way harder because you have that additional constraint. The source code you produce must not just be executable and equivalent. You have a constant chase for maintainability, for structure, and for quality. So when people want to translate from one language to another, obviously they want to get rid of whatever they had for reasons that have to do with obsolescence. We're talking about aging languages that may not be available on modern platforms, or may be too expensive, or maybe too hard to find resources for. And because they feel the burden of legacy, they want to go to something that they perceive as being foolproof, something that will stand time. And in that context, I assume that Java and C# are good candidates. So it's a common question that comes to us. Can you translate this into Java or this into C#? And the whole point about this talk is to give you some insight about the experience we gained in those projects. Among the transformation that you can perform to post-process the output of your translator, there are many things. There's pretty printing, there is reformatting comments, there's getting rid of dead code. You can, for instance, get rid of unneeded parentheses in order to make your expression look neater. It can be really, really low-tech stuff. But we don't do it just for fun. We do it as to allow the translation process per se, which is the most critical part of the process, where you go from language A to language B, to be as simple as possible, and to focus on, okay, I need to produce something that is executable. It may not be ideal. Someone else will, another process, should I rather say, will clean up the resulting code afterwards. And that simplifies the translation process. That's the whole point of that entire infrastructure, simplifying the translation process. So now let's get to the meat of this talk. We're going to visit infamous features of C#, features that are documented but barely so, features that that application developer should not use, features that application developers are even instructed not to use. The truth is, features that most application developers do not even know about C#. I call them dark corners for a reason. First things first, the infamous go-to statement. Don't get me wrong, you won't find anyone more radical about go-to statements than I am. If you ask me, I get rid of go-to statements altogether, and not just go-to statements per se, but also hidden go-to statements, like getting out of a function from the middle of it, or getting out of a loop from the middle of it. I think that I strongly believe even that structured programming should be promoted at all times. This is not about what I want. This is not about my ability to change something about the code I'm writing today. This is about me receiving a piece of code, a large piece of code written in some kind of idiotic language, and I have to translate it. And there's only one thing that is even worse than go-to statements, is whatever you're going to replace go-to statements by, if you want to get rid of them, or if your target language does not support them. I know that you can do something really smart and freakingly annoying based on non-local go-tos or exceptions or those kind of things, but that will make your code so 1,000 times worse. So this is not me telling you that go-to statements are good. I'm just saying that in my world, I receive those go-to statements. I have to do something about them. And the fact that C# essentially supports go-to statements means that I have a one-to-one mapping, and I can produce something which is not ideal in my view. I fully appreciate that, but it minimizes the entropy, it minimizes the added complexity in the process. And I'm giving this example with go-to. You'll see this, I'm going to be repeating myself because this is going to be a common thing. So all these things in the dark corners are features, most of them at least, are features that I would really not advocate for people to use ever. But when I translate, it makes my life so much easier to have something fairly straightforward to translate to, rather than have to emulate it, because that would make it 1,000 times worse. So C# supports go-to statements, Java does not. And this is also going to be a pattern throughout the rest of this talk, where you see, well, those things that are excluded from Java for very good reasons, and are included in C# for what I would claim are good reasons. They are very different reasons. In the same vein comes operator overloading. Again, I'm really not crazy about operator overloading in general. In theory, you can see the beauty of it because it allows you to use your language as a meta language to deal with your data type with operators that make sense from a mathematical point of view. So that's really cool. And we've all seen those examples with the complex numbers where you can say, oh, I define my own complex number class and I have my operators, and that looks beautiful. And we've all seen how that thing goes wrong when people start misusing operator overloading like all over the place for the sake of saving keystrokes as if that was a thing. And you end up having something that is crazy hard to understand. And at the end of the day, bear in mind, this is exactly what we're all about: producing software that a human reader can understand. And there is no simple way to assess that operator overloading has been well used, has been used in a place where you say, okay, you actually map to something that makes sense mathematically, so there's a case to be made. You have no way to assess it, so I really prefer to go on the safe side and say, well, I'd rather not, if at all possible. But this, again, is about my position when I write software. When we are in the process of translating software, the source language may, and often has, data types that we do not support, that are not supported out of the box in the target language, and we need to define matching data types in the target language. And when we do that, we need to be able to, we don't need to, but it's much better to be able to define operators so that the resulting code looks so much more like the original one. Remember what I told you before about having two different sets of populations to please. This is really in the spirit of saying, listen, you've been maintaining this code for thousands of years, for years in the original language. Now you'll be able to maintain it in the target language and it will look similar. And operator overloading is very useful in that sense. And again, I 100% concur with the reasons that the Java community uses to justify why Java does not and probably will not support operator overloading. But again, their use case is a very specific one, and mine, well, is a different one. A little bit less controversial are C# structures. C# structures are essentially, let's say, aggregate data types with a value-based semantics. So they're not heap-based, they're going to be stack-based. And they are very useful for high-performance systems where you don't want to overuse dynamic allocation and put too much pressure on the garbage collector. Structures don't have that negative image attached to, say, go-to statements or operator overloading, but the use case in normal software developments are really narrow because you really have to be in a situation where reference-based semantics is toxic and where you need it to be stack allocated for performance reasons. I won't say it never happens, but it's not the vast majority. The vast majority of the case, you can define everything with classes. What's really nice in our world, where we translate from one language to another, is to be able to take advantage of this value-based semantics. We don't have to worry for references and for aliasing, which is the normal side effect that comes with reference-based semantics. And together with operator overloading, it allows us really to define fairly sophisticated composite data types and have them integrated in the target language pretty nicely. But it's not as controversial. I mean, using structures is not something where people say, oh, it's evil or it's bad. It's not as much of a dark corner as some of the other features are. So far, we've dealt with fairly straightforward stuff. Now we're going to dig into the really, really dark corners of C#. A few years back, C# started supporting a dynamic data type. And very bluntly, they said that this was something that was designed specifically to allow C# code to interact with dynamic language. I think they mentioned Python or Perl back then as reasonable candidates. And the whole idea about those these dynamic data types is to defer at runtime things that compiled language, such as C#, typically perform at compile time, namely name resolution. For instance, look at this piece of code. In this piece of code, I declare a variable and I consult an attribute and I call a method. Nothing new under the sun, apparently, because in fact, what's happening under the hood is very, very different from the normal C# behavior. I took that piece of code, I compiled it, and then I disassembled it. And this is what is shown here. There are quite a few technicalities in this piece of code, and I don't want to get into the intricacies of the MSIL intermediate language and how it works, but what I want to emphasize is the fact that instead of having the name of the attribute resolved at compile time and turn into, well, a static attribute access in the generated code, you can see in this piece of disassembled code that the name of the attribute is represented as a string. And the whole idea is that the function that will, out of this object and this string, return you a value is 100% under your control, which means that you can change that behavior. You can make it work any way you want. And interestingly enough, the same goes for methods. What I mean, you can actually have a method that does something or that does nothing, that starts processes, that reformats your hard disk if that's what you want. You can essentially change the behavior of your language because you can capture access to attributes and method invocations and put whatever kind of semantics you want behind them. And this is probably, in this entire talk, the place where I'm trying to give justice to the title, say, well, you can use C# as a meta-language to produce something which is, quote, a language with a fairly different kind of semantics. Granted, you don't change the syntax, but you change the underlying semantics within the syntax in a way that, as far as I know, no other language supports today. And even though C# is a statically compiled language, you have a way of saying, well, you know what, I'm accessing an attribute. You, as a compiler, you're not responsible for resolving this. And this is what makes C# a generative tool to produce ad hoc languages. And again, in this context of migration from one language to the other, when we're translating fourth generation language that can have fairly dynamic capabilities, this is obviously a bonus. The alternative would be to have awful getter and setter function that would all pass everything like strings. It would work. It would essentially be the very same behavior, but it would make the resulting code much harder to read and to maintain. This is more of a detail, but it's a nice one. C# also supports a concept called partial classes. And at first sight, you wonder, why would you need this? Partial classes are just the ability to take the text of a given class and split it over multiple source files. And in a normal environment, normal development environment, you should never need this. If your class is so big that you feel the need to split it in more than one source file, as I say, there's something rotten in the world of design. There is something wrong. The whole point about object orientation is to allow you to design your system into manageable pieces. But this is not about size. This is typically useful when you have a class where a part is generated and a part is handwritten. A part is generated, is tool generated, and may have to be regenerated often, and the other part is manually written and maintained. And the ability to have two separate source files for this allow you to regenerate the generated part whenever you want without overriding whatever manual changes you made on the other side. In Java, there's a strong insistence on saying, well, every source file can contain up to one public class. And it's a very sensible design rule and a way of saying, well, the physical mapping on the file system of your software maps its structure closely. That makes it easier to navigate. And that's 100% true. But it does not account for scale. Sometimes that kind of rule is really getting in the way. I had a case where we had 7,000 entry points, call them procedures if you want. We had 7,000 entry points. And that was ugly enough, the truth is. But it was even worse because each of these 7,000 entry points had one input class for parameters and one output class for, well, output parameters, which means that a trivial mapping onto Java would have produced 21,000 source files. And I submit to you that that is way too much. That is really, really, really unreasonable. So these are cases where having a little bit more flexibility on how you map classes to source files, the way C# does, can actually be very beneficial. I appreciate the rationale behind Java's insistence, but you see how these kind of dogmatic rules can really break under pressure and under scale. Last but not least, C# supports pass-by-reference or output parameters, which pretty much amounts to the same. Again, Java makes a very compelling case on why all parameters should always be passed by value. It makes for a cleaner design. It makes for a simpler implementation. It means that the only statement that can change a variable's value is an assignment in the scope where this variable is seen, which allows for better control. The truth is, Java should not push that case too much, because with the use and overuse of the reflexive API, there's so many ways you can circumvent this, but let's not go there right now. So, but Java has a case, and when claiming that all parameters should be passed by value. But again, this is not about software we develop. This is about translating existing software in existing languages into something, and to minimize entropy, to minimize the added fact, to minimize the added complexity in the process. And if the source language, or more importantly, the source system, uses and overuses pass-by-reference, then it's tricky if the target language does not. So I can hear you say, oh, but that is easy to solve. You just have to box your elementary data types into classes. And that's true, it's feasible. But in the spirit of having something which is native to the target language, you want the system to be native C# or native Java whenever possible. You really don't want integers to be encapsulated into something if you can avoid it. Or worse, strings. Strings are pervasive in those applications. Encapsulating strings and say, well, you won't be able to use strings. You're going to have to use our strings because we must be able to pass them by reference, and so on and so forth, is not a very compelling proposition. So in conclusion, I hope I made my case clear. Java and C# are more different than meets the eye. From a purely application development point of view, I really appreciate that they are very, very similar. For my very specific use case, where I need to translate existing system into Java or C#, the different sets of features provided by both languages make for a very, very big difference. Don't get me wrong, I'm not advocating that in absolute terms C# would be preferable to Java. I don't have the bandwidth nor the religious anima to defend one of those cases. I just say that in the case of translation from one language to another, C# is a much more flexible proposition. So when customers come to me and say, well, can you translate this to Java? I usually have to say, well, we can, because at the end of the day, they're both Turing-complete languages, and this is not about the ability to produce something executable. This is even barely about the ability to produce something executable with adequate performance. This is just about the added entropy to the system. So I have to tell customers, oh, you want to go to Java? That's fine. But if you go to Java, there's going to be this and this impact on quality. You're going to have thousands of source files, or you won't be able to use strings, or your operators are going to be translated into function calls. And if you're okay with that, I'm okay with that. But bear in mind, it's your responsibility from now on. And I have a little cherry on the cake, a pragmatic one, which I really like, and something that makes C# a really compelling proposition here. Remember that picture where I said, well, we're going to do pre-processing transformation and then post-processing transformation, because you don't do that as a single operation. So if we are to do post-processing transformation in C#, there is a fantastic tool named Roslyn made available by Microsoft. And Roslyn is essentially a set of components that implement a complete C# compiler, and that you can reuse piecemeal, so that anything that has to do with analyzing C# code, lexically, syntactically, semantically, transforming it, and even serializing it, is done by Roslyn. So you have a fantastic ability to implement highly sophisticated tools from C# to C#, which is exactly what we try to do in that picture where we post-process the code. And even fairly sophisticated stuff like, getting rid of dead code that in other circumstances could be really complicated to implement on your own, using Roslyn can be fairly straightforward. So that's one of the reasons why I really like C# as a target language there. In all fairness, there has been, I think 10, 15 years ago, an initiative on the Java side called Jackpot that did pretty much the same. And I would even, I wouldn't be surprised if someone told me that Roslyn was to some extent inspired by Jackpot, because Jackpot had really a very neat API for these things. But Jackpot has pretty much gone into oblivion. I mean, I think they're now they're part of NetBeans, and I'm not sure how well maintained they are. I mean, perhaps they've been following up with the new evolutions of the language, but to be candid, I would really be surprised if they did. Well, that's it for me today. Thank you, and have a great day. Bye-bye.